Chapter 2, Section 2 is on subsets. Now, I mentioned subsets in the last video from 2.1 when we talked about the universal set, but we did not get the notation for subsets. Notice that we have subset and proper subset both listed. A subset, I would say A is a subset of B. My pen has issues sometimes. That subset symbol needs to be like a union symbol on its side with a line down below because it can be or equal to. So that's a better subset symbol. There we go. A is a subset of B. Now, remember, notice what I just said. It's got that line below, and that line below always means or equal to. So this is my general subset symbol. A is a subset of B. If and only if and only if, and that's kind of a mathematical phrase that means it works both ways. If and only if all the elements of set A are also elements of set B. So A is a subset of B if and only if all the elements in A are also in set B. Now, in general, we can say this general subset, the two can be equal to each other as well. But if I have a proper subset, then my symbol is a little different. This is my proper subset symbol. What do you notice is different? Well, it does not say or equal to. So it's a proper subset. Set A is a proper subset of B, if and only if, and we're going to start with this definition. All elements of set A are also in set B, but additionally, A cannot be equal to B. That means that B has to be bigger. B has to contain at least one more element than set A. So to be a proper subset, for A to be a proper subset of B, all of the elements in A also have to be in B, and there has to be something else in B that's not in A. So we have, well, here's an example. Back to my grocery store example, Kroger. If my universal set is Kroger, let's say that's set B. So if set B is Kroger, everything for sale in Kroger. Set A is the freezer section, anything in the freezer. Then I can say that A is a proper subset of B because everything in that freezer section for sale is also for sale and generally in Kroger. But there are things in Kroger that are for sale that aren't in the freezer section. So A is a proper subset of B. Okay. Consider the sets below and write the correct notation. We have A, B, C, and D defined. Are any of those sets equal? Well, yes. Notice that A and C are equal sets. D is equivalent to A and C, but it's not equal because it doesn't have the exact same elements. Okay. Let's read the first one. Set B. Is A a subset of B? Well, A and B, if I compare them, yes, I can say that A is a general subset of B because all of the elements in A are also in B. Is A a proper subset of B? Are all the elements of A in B and B also has an additional element? Yes. So A is a proper subset of B. You see the difference in the notation. All right, let's look at the next one. Is A a subset of C? A is 1, 2, 3. C is 2, 3, 1. Yes. A is a general subset of C. Is A a proper subset of C? They have the same elements. Does C have at least one additional? No, it does not. So I would say that A is not a proper subset of C. And then finally, is A a subset of D? Well, A has 1, 2, 3. D has 2, 3, 4. No, all of the elements in A are not in D. So A is not a subset of D. And since it's not a subset, it definitely cannot be a proper subset. So A is not a proper subset of D. Then we're asked a question, when is a subset not a proper subset? Well, a subset isn't a proper subset when they are equal. My pen jumps. When they are equal. If they're equal sets, they contain all the same elements. For a non-empty set H, could we say that H is a proper subset of H? Non-empty just means it has elements. It's not the null set. So can H be a proper subset of itself? Well, no, because H is going to be equal to H, which means that it can be a general subset, but it can't be a proper subset. Let's apply our set theory to some Venn diagrams of sets. Here we have two different Venn diagrams. We have a Venn diagram with set C and D, and we have a Venn diagram with set A and B. This first Venn diagram has one set completely inside the other. Set D is completely inside set C. For A and B, though, they are just overlapping. They share some things, but everything in A is not also in B. For example, set A includes 1 and 2. 1 and 2 are not in the set B loop. Set B includes 6 that is not in set A. They do share the elements 3, 4, and 5, though. Up here for set C and D, D includes just these 3 elements. These 3 elements are in the D loop, but set C has a bigger loop. It includes those 3 and these other elements here. So down at the bottom, 1, 2, 3, and 4 says to identify the elements in each set using the roster method for all. And then we're going to do set builder notation on sets 3 and 4, or on number 3 and 4. So what are the elements in set C? Set C is going to include everything in the set C loop. We're going to do least to greatest so that it's easier for us to compare our results. Set C includes 2, 4, 6, 8, 10, 12, and 14. Every one of those elements that's inside the C loop. Set D just includes the elements inside the D loop. So set D just includes 4, 8, and 12. Then I go to set A. Set A includes 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, roster form. Set B includes 3, 4, 5, and 6. Because those are the elements inside that set B loop. Now it challenges us to use set builder notation as well for numbers 3 and 4. So for set A and B, we need to do set builder notation to practice that. For set builder notation for A, we start out the same way. A is the set of all elements X such that, and then I notice that these are counting numbers, so I'm going to say X is an element of the natural set. Then I need an inequality statement that represents 1, 2, 3, 4, 5. I can say that X is less than or equal to 5, or I could just say X is less than 6. Either one would be correct. So for B, when I do set builder notation on B, I start out B is the set of all elements X such that, again, I see I have counting numbers. So X is an element of the natural numbers. And then I need an inequality statement. I have a middle here. I have a starting place that's not 1, and then I have an ending place. So I'm going to set up a compound inequality. X is greater than 2, or I could say greater than or equal to 3. Either way, that's my boundary at the lower end. My upper end is 6. Let's say less than or equal to 6, or I could have just said less than 7. So there's my set builder notation for 4. Okay, now we're asked some questions about these sets, A, B, C, D. See if I can get them all in. First, we're asked, true or false, D is a general subset of C. Well, is D, everything in D also inside C? Yes, that is true. Then number 2 says, C is a general subset of itself. Well, that's true. C is a general subset of itself. It wouldn't be a proper subset of itself, but it's a general subset of itself. C is a general subset of D. For that to be true, every item in C should also be in D, but you see that we'd have elements out here in C that are not. So that is false. That is not a correct way to state that. Number 4, everything in A is a general subset of B. Well, A is not inside B. Part of it's shared, but not the whole thing, so that is false. And the same is true for B being a subset of A. B is not inside A, so that is false. Finally, B is a general subset of itself. That's true. Not a proper subset, but a general subset. Can a set be a subset of itself? Yes, a general subset, but not a proper subset. It can be a general subset because of that or equal to line. And finally on this page, which Venn diagram would represent the subset relationship? The overlapping circles like A and B, or the circles where one is inside the other like C and D? Well, if you look at our answers to our questions, we see that C and D, we have a subset relationship where D is a subset of C. So the one inside the other, that's the option that we want to select, like C and D above. Okay, let's look at the next page. Note that A is not a subset of B. That's how that's read. A is not a subset of B. Given the sets below, fill in either a subset of or not a subset of. So you've been given subset roster form for C, D, E, F, and G, and you're asked to fill in one of those 2 symbols for 1 through 4. Pause your video, answer those questions 1 through 4, and then come back. Okay, see if your answers match mine. Basically, C is a subset of D because all of the elements in C are also found in D. And C is a subset of G because all of the elements in C are also found in G. But C is not a subset of E or F because C includes an 8 and neither E or F includes 8. I could further say that C is a proper subset of D because D includes more elements. But I can't say that C is a proper subset of G because they are equal. I could turn around and say that F is a subset of C because all of the elements in F. Oh, that's not true. That's a false statement. I'm sorry, I was looking at E. I could say that E is a subset of C, not F. F would be a subset of D because all of the elements in F are also in D. And F would be a proper subset of D because D includes more than what is in F. All right, remember cardinal number tells us how many elements are in a set. It can also help us figure out how many subsets there are. We're going to do a little bit of an investigation by writing out ordered lists. the question is, how could we determine how many subsets a given set has based on its cardinal number or the number of elements it has? So we're going to do this. We're going to determine the cardinal number of each set, list out how many subsets there are, and remember that a set is a subset of itself. We're asking for general subsets, not just proper subsets. Okay, so my first set is the empty set. The cardinal number of the empty set, I don't have a label for these sets, do I? So let's do A, B, C, D, E. Now we have labels. The cardinal number of set A is 0. If I break nothing into subsets, the only way to do that is to have the empty set. Oops, I nearly put something inside of it. Let's turn that, let me make that better. There we go. The empty set. So I only have one subset. The empty set is a subset of itself. Okay, so let's look at set B. Set B has A as an element, so the cardinal number of set B is 1 because it has one element. Now, the empty set is a subset of every other set. I can pull out nothing if I want to. So I'm going to start by listing the empty set. And then I'm going to put A inside. So there are 2 possible subsets. Let's look at set C. Set C has 2 elements. So the cardinal number of set C is 2. Now let's break set C into subsets. Well, empty set first, and then I can include just A, or I can include just B, or I can include both A and B. So I've got 1, 2, 3, 4 possible subsets. Let's do that. Let's say we have 1, we have 2, and we have 4 possible subsets. All right, set D. Same thing, I determine the cardinal number. I have a total of 3 elements. For set E, I would have 4. And then I'm going to pull out as many subsets as I can. So go ahead and break this up. You're always going to start with the empty set. And then I can take the elements one at a time. So I've got just A, I've got just B, and I've got just C. Then I can pair them up. So I could do A and B, and then I could do A and C, and then I could do B and C, and then I could do all 3. So A, B, C, which gives me 1, 2, 3, 4, 5, 6, 7, 8 subsets. Do you start to see a pattern going on over here? I've got 1, 2, 4, 8. How many subsets do you think we might have when I have 4 elements? Let's look and see. So as always, excuse me, I can start with my empty set and then one at a time. So just A, just B, just C, just D. And then I can take them 2 at a time. So I could do A, B, A, C, A, D, and then go back and pick up B, C, and B, D, and then C, D, and then I can take them 3 at a time. So I could do A, B, C, or A, B, D. I could do A, C, D. I could do B, C, D. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh, and I can do all 4. A, B, C, D. So I get a total of 16 subsets. Now, if I had 5 elements, if I did one more time and I had 5 elements, how many subsets do you think I'd have? I'd have 32. Hopefully you notice that I'm multiplying by 2 each time. So that when I had a cardinal number of 0, I only had 1 subset. Then when I had one element, I had 2. When I had 2 elements, I had 4, and then 8, and then 16. So what's my general rule? What am I doing here? Well, if it's been a while since you've dealt with exponents, it may be a little difficult to see. But 2 to the 0 power, anything to the 0 power is 1. 2 to the first power is 2. 2 squared is 4. 2 cubed is 8. What do you think this one would be? Well, 2 to the 4th. Where am I getting those exponents from? They come from the number of elements in the set. So depending on the number of elements, whatever that value is for the cardinal number, I can solve 2 to the n power, and it will tell me how many subsets. Now, we did this by using inductive reasoning. We took a set of examples. We did n equals 0 to n equals 4. That's 5 examples. And we formed a general conclusion. When I use inductive reasoning, can I prove my conclusion? No, I cannot prove inductive reasoning because I would have to try every possibility, and there's no way to do that. So let's think about this. Just to make sure you understand how it works, if I had a set with 7 elements, so that maybe I've got the cardinal number of set Z has 7 elements, then that means that the number of subsets would be 2 to the 7th power. And I would have to work that out to figure out how many that was. So if you look at your calculator, I have this arrow, looks kind of like a little housetop. That's my exponent button. So if I want to do 2 to the 7th, I type 2, push that button to the 7th power, and it tells me that would be 128 total subsets. Now, when I look at these, and now this gets to the next page. So let's go ahead and look at the next page and see what the question says. The formula for the number of subsets we just discovered is 2 to the n. How many subsets of a given set are not proper? Well, a subset that is not proper is when it is equal to the original set. So for example, right here, these are equal to each other. So there would be 1 total subset, but 0 proper subsets. Right here, this is equal to the original. So even though there's 2 total subsets, only one of them is proper. For C, this AB is equal to the original. So there are 1, 2, 3, 4 total subsets, but only 3 of them is proper, because that is not proper, not proper, not proper, because that is equal to the original. Not a proper subset. So notice that the one subset that is equal to the original is not proper. So all the rest of them are. If I have 8 total subsets, I have 7 that are proper subsets. When I have 16 total subsets, that means 15 of them are proper subsets, and 1 of them is not because it's equal to the original. So, how many subsets of a given set are not proper subsets? Well, just that one, because that one is equal to the original. That means it's not a proper subset. How could I adjust that formula to show the number of proper subsets? Well, I'm going to take that total, 2 to the n, and I'm going to subtract 1 from it. And that tells me how many proper subsets exist. Because I get the total number of subsets, so I say, okay, 1 of them is equal. That's not a proper subset. So when I did 2 to the 7th, if I have 7 elements, there are 128 total subsets. Only 127 of them are proper subsets because I have to subtract the one that is equal to the original. Okay, here's some practice on this. Use your formula to determine the number of subsets and proper subsets for each set below. Set S has all the elements x such that x is a day of the week. Well, how many days of the week are there? That tells us how many elements there are. There are 7 days of the week. Oh, we know the rest of this, don't we? So to get the total number of subsets, I do 2 to the 7th, which we figured out is 128 total subsets. And out of that, how many are proper? Well, one of them is not, so that leaves me with 127 proper subsets. I'm going to pause the video and answer the final 3 questions. You do the same. Okay, let's come back and finish this. For set T, all elements x such that x is a natural number and x is greater than or equal to 2, less than or equal to 6. So if I list the roster form for T, I go from 2 to 6. 2 is my starting place, 6 is my stopping place. I have 1, 2, 3, 4, 5 elements. So the cardinal number is 5. To figure out how many total subsets, I do 2 to the 5th because that's n, and I get 32 total subsets, which means there are 31 proper subsets for set T. For set V, I have set builder notation, all elements x such that x is a natural number and x is greater than 3, less than 15. If I come over here to do roster form for V, greater than 3 would start at 4. And where do I stop? Well, less than 15 means I have to stop at 14. When I list all those out, I see that I have 11 elements, so the cardinal number for set V is 11. And to solve the total number of sets, I do 2 to the 11th power. In my calculator, again, I type the base, the 2, use my exponent button, the little house top, and type in the exponent, enter. It gives me 2,048 total subsets, and out of those, only one of them is equal. The other 2,047 are all proper subsets. And finally, W is the set of the months of the year. Well, there are 12 months in the year, so I do 2 to the 12th is 4,096 total subsets. Only one of those is equal to, so the other 4,095 are all proper subsets.